Okay, so I haven't adjusted due date, so I think the exponential functions, that homework, let's go ahead and keep that one at midnight. This one we may adjust, though. We're still talking about this a little bit, and we have a couple more problems to do off of that one. So we may move that back slightly. And then we have... we're starting a different section today. I don't have the homework posted for that one. That one will, that's I think the last homework that's due prior to the test. Although I may post other homeworks prior to the test. I think the last one that will be due is just one additional assignment. Of course, in addition to these two, right, that have been up there for a while. That one's just extra credit. Those are due at the time of the test. So we're right on track, sort of, for the, I think, let's see how far we get today. I think we're right on track, though, for the test next week. So we should be in good shape. Don't forget now, on the class webpage, right, the sample test is posted, right? So so you still have a lot of time to work on that, right? That's not something you're turning in, correct? That's something to prepare for, to use to prepare for test number 1. And at some point, I'll post the answers, but not immediately. Okay, so it'll be a little while before I get around to posting the answers, because I want you to work on that independently of having the answers available to you, right? So you can take this to the Math Center or get help any way you like on this one. That's just preparation for the first test. Don't forget to fill out your index card, though. So be thinking about what you want to put on your survival card. All right, so just the very act of thinking about what should go on the survival card, what you need on there and what you maybe don't need on there, that itself is a good review for the test, okay, because that makes you go back and think about all the different formulas you've used, right, or all the examples that are important to you, right, that you might want to include on the survival card, what's crucial for it to go on there and what's not. That helps you prepare for the test, right? So don't neglect to make that out. That will be useful to you, I think. Even if you end up not using it very much when you're sitting taking the test, all right? Sometimes when you make out the card, you end up memorizing a lot of stuff on the card anyway. But making it out is good practice. So so work on that too. Okay, so before we try to finish the notes for this section, log bases other than e, we're not going to be running into log bases other than base e or exponential functions other than base e that frequently, but nevertheless, we want to cover that topic. But before we get back to that and finish that, we have a few more problems on that notes. Any questions about that exponential functions homework that you want to ask? Yeah, Janaya. Okay, so let's see if, all right, let's see if we can, if y'all had problems, I may have problems too, so, but Taylor may help us if we're, oh yeah, okay, so that one we haven't had an example of, so that, that's a fair question because I don't think we have. All right, well, this is a good problem. Okay, so that one's, that's going to be one of the harder ones. So I think you know all of the, I think you know all the pieces of this, but it's just, that's a pretty complicated function, and then trying to put all the pieces together makes this just a challenging problem. It's just a lengthy problem, but kind of similar to the Calculus 2 problem in terms of the complexity. All right, this actually is quite a useful problem. It has applications outside of Calculus 2. It's actually instructive to make the graph of this, but you don't need the graph to answer the question, but it's really helpful to look at the graph. So we'll make a graph here. You're going to have to help me construct that graph we'll use Desmos to construct that graph. Do y'all have, before we launch into this one, are there others, though, that I need to be thinking about? What? 15 also, okay? Is that the, maybe that's the differential equation problem. Right, okay, so, yeah, I was anticipating that one as well. All right, so that also is one that, this one we haven't really seen an example of, so so this one really is good to look at. This one we've had an example of. It's just a matter of you know, executing all the steps here. Okay. All right. So let's write that down. This my version of the problem might be slightly different from yours. So can y'all help me write that down? So someone write that down. So because I've got to switch notes here. Okay. So I can find some maybe some blank paper to work on. Did someone get that written down? And let's work down here. So that function was g of x, right? So it's g of x is 1 over square root of 2 pi. So a very strange coefficient there, right? And then e to the, what is it, minus x minus 8. Make sure I got all the minus signs there. Minus x minus 8 squared. So be careful here. The x minus 8 is squared, but the minus sign is not, right? So that's not going to end up being a positive exponent there. And then all of this is divided by 2. So all of that is the exponent, right? Okay. For that function. And so we're trying to find the local minima, right, and the local maxima, so the turning points on that graph, and then the inflection points. So as I mentioned there, it really does help to look at this, to make a graph of this, just to convince yourself that we're not wasting our time, right? We want to see in the graph if we really do see some turning points, or if we really do see some inflection points, right? So we'll have an idea that you know, we really have you know, answers here that we're really looking for. So let's bring up Desmos. So again, the link here is at the top, either in the instructions or the description. Sometimes I put it in different places, but there it is in the instructions. So let's click on that link, and let's see if we can graph that function. So when you open this screen, you just get this. This is just this basic curve graphing screen. So all you have to do is type in the formula for the function, and then it's going to make a graph here on the right-hand side. Now, keep in mind, you might have to adjust the graphing window a little bit, though. Okay, this is just set to some just some arbitrary size. By the graphing window, I mean the portion of the x-axis you're looking at, right, and the portion of the y-axis you're looking at. So right now it looks like it's set to fit this function, but that function was just an example function, right? So let's type over that, and so it may be just a challenge to get that formula typed in. That may be itself kind of tough, right? So I want 1 over square root of 2 pi, right? So I think you can get a fraction. All right, so there we got the fraction, right, just by hitting the slash on the keyboard there. But I think also on Desmos you have this keypad at the bottom that you can access to type in, special symbols and so forth. Right, so it's 1 over, and then let's see, we want 2 pi, right? And then the square root of that. So let me type that as 2 pi to the 1/2 power, but I think it may change that to square root for me. I'm not sure. So, but to get 2 pi, just type in the 2, of course, and then times pi, right? So let's just type in pi and see if it. And it knows pi, so I just typed in the letters pi, right? That's the Greek spelling of pi, and so it converted that to pi for me. And then let's raise that to the 1/2 power. So that's I'm going to hit the caret key to get an exponent, and then 0.5. Maybe that's the wrong way of, whoops. So there's 1/2 power, but we can also get square root. We may have to get that from the keypad. Let's see if I highlight that and go to the keypad. Is there a square root in here? Oh, there it is. All right. Well, I lost my 2 pi, but we can put that in back in pretty easily, right? That's a little bit too big. All right, okay, so there's finally 1 over the square root of 2 pi, right? And then Desmos knows e, right? And now you're raising that to a power, so I'm going to hit the caret key to get an exponent here, and let's see, what's the power? That involves a fraction, doesn't it? And then it's what, minus, and then in the parentheses, x minus 8, right? And all of that we want to square again, and then so I hit the caret key again, the shift of the 6 key, and then we divide that by 2. Okay, so I see something. Now I like that better. All right, so not a good graphing window for this graph, but you can see something, right? So that means that we can focus in on kind of the interesting part of the graph by changing the graphing window some. Remember, you can do that through the settings up here, so you can actually set the portion of the x-axis you want to look at and the portion of the y-axis you want to look at. Or you can just drag the screen around and zoom in. So that may work for us here. Yeah, that's not bad. We can get that a little bit better if we individually set the x and the y axes. But this is okay to look at, because all we're trying to confirm here, right, Janai, is that we don't have a bogus question, right? So we want to make sure that we have what? A maximum or a minimum, right? Okay, so a local maximum or a local minimum. So that means it's either a peak turning point or a valley turning point. And we do have the peak turning point, and it's a very convenient location. It's right at 8, all right? So that's nice. So that's, I think, going to be easy for us to find analytically with pencil and paper. Okay, and then harder, though, maybe harder, are going to be inflection points. Does this thing have any inflection points? Now, you may not be able to locate them very well by eyeball, but can you tell that they're there? So, again, what happens at an inflection? This is really crucial, because we don't work with inflection points as much as we do turning points, but they're still important. So, yeah, the concavity changes, right? Okay. Remember, the concavity is curvature. That's the fancy name for curvature. So we only have 2 concavities. So we have curved up, that's concave up, and then we have curved down, that's concave down. And the concavity changes at an inflection point. So we are going to have some inflection points here, right? Because the left part of this curve is concave up, and the middle part is concave down. So that concavity had to change somewhere about right there. It looks like it might be at 7, right? Okay, yeah, 7 actually might be it. I'm suspicious that 7 might be it, but we'll have to see. Okay, and then there's a reason why I'm suspicious, but and then also maybe over here at 9, right? See, the concavity changes from concave down to concave up, so that happens somewhere about right here. Maybe it's 9. Okay, could be 9. This type of curve has important applications. This is a bell-shaped curve. So we use bell-shaped curves a lot in mathematics. The term bell-shaped curve kind of has bad connotations now, okay? But that's the name of this curve. It's a bell-shaped curve, and they're important in statistics, okay? In probability and statistics, because we often think of the area under the bell-shaped curve as representing a population of objects. Often people, okay, but it could be other objects as well. All right, and then the nature of that area under that bell-shaped curve helps us answer statistical questions about that population. All right, so this type of curve is very useful to us, and the inflection points are important in bell-shaped curves. Okay, so that's why they're having us look for these inflection points. Okay. All right. The turning point is also important too. All right. So let's go back here now. So we've just looked at the graph. So that gives us some reassurance here, maybe of what we're expecting our answers to look like, right? And now let's go about finding the answers. So how do we look for the turning points? Find the derivative, right. And then what do you do with the derivative? Set it to 0, right, because a turning point is going to occur where the tangent line is flat, okay? You have a flat tangent line. Remember, the slope of the tangent line corresponds to the derivative, correct, okay? So you're looking for where the slope of the tangent line is 0, where you have a flat tangent line, and that means where the derivative is going to be 0. So that's why we set the derivative to 0, right? See in the picture, and you've seen this picture lots, I know, okay, in Calculus 1. In the picture, right, you're going to have a horizontal tangent line, right, at turning points, correct? Right here, you can see that horizontal tangent line, right, at that turning point right there at 8, okay? So that's why we set the derivative to 0. Now, how do we look for the inflection points? Similar process, right, except second derivative, right, okay, except now we use the second derivative. So finding inflection points is no more difficult than finding turning points, except you have to find the second derivative, and sometimes that's a little bit messy, but let's see what happens here when we find the second derivative. But first things first, let's start with the first derivative. So we want to find g prime of x, right, and then set that to 0, okay? So notice what you're differentiating here. Get lucky, you're differentiating basically an exponential function. Don't get confused by this nasty coefficient here. This is just a number, okay? I don't know what 1 over the square root of 2 pi is. We could estimate it with our calculator, but that's just a number. So we have a number here times, and this is just an exponential function, right? Because you've got e raised to an expression. So, so we're just following our rules for differentiating exponential functions, which is really easy, right? What do we do to differentiate exponential functions? Natural exponential functions, I mean. What do we do? Fortunately, this is not base 2 or base 10 or something. This is base e. So with a natural exponential function, what do we do? What now? I don't think natural log is going to show up here, okay? Yeah, so, no, we don't need substitution. We're not integrating, right? Okay, we are differentiating, okay? So that's going to be a little bit easier, right? But so here's just a rule of thumb. You need to remember this. So I've said this a lot, but you need to sort of internalize this now. Okay, when you're differentiating the natural exponential function, the key thing to remember is what gets repeated. Just the function, right, okay? The function just gets repeated in the derivative. You really got to remember this for a test. If you don't remember this for a test, then you're not going to be able to finish the test in time, okay? Because that should be really an easy type of problem. So you've got to sort of do quickly, okay? Or you won't get finished with the test. So you just repeat the function here. That's kind of the key part of the derivative, but that's not the only part of the derivative, because what's going to also come into play here, as it frequently does with derivatives. Yeah, the chain rule, right? You must now multiply in the derivative of this expression. If this were just x, we would be done. But it's not. It's a lot more complicated, right? It's minus x minus 8 squared, so I have to multiply in the derivative of that. Ugh. All right, so how do I take the derivative of this? So I've got to think of more of my differentiation rules. How do I take the derivative of this? What differentiation rule are we using here? Don't need the quotient rule. You could use the quotient rule, but it's not necessary here. You're going to make it too hard. But what key rule here are you going to use? Begins with a P. Not the product rule. Okay. Another P. What? Power rule, right. Yeah. You're going to use the power rule. Why the power rule? Duh. Because what? There's a power. Yeah, sure. So we're going to use the power rule, right? Okay. This is why you won't need the quotient rule. When you apply the power rule, what are you going to do with that exponent? Bring it down. What's going to happen to that 2 and this 2 then? What? Cancel. So you see, you won't have a fraction anymore. So you don't need the quotient rule. See. So you bring the 2 down, and then these 2's will divide out. Now don't forget, this itself is an expression, right? So you may have to apply the chain rule again, a second time. But what's the derivative of x minus 8? 1. So fortunately, the chain rule the second time is irrelevant. All right. Remember, chain rule it's not called the chain rule for nothing. Sometimes you have to apply the chain rule in a chain. You see, okay? You have to apply it multiple times in the same problem. All right. Well, let's do that then. So we multiply in here. Let's see. Y'all told me we brought down the 2. This 2 canceled. And so I think I just get what? Is it just minus x minus 8? Is that it? Yeah, that's it, right? Okay. You brought the 2 down, subtracted 1 from it. So this is x minus 8 to the 1 power, right? The 2's canceled. You still have the minus sign here, though. But now, and then the second version of the chain rule is, the second application of the chain rule is you multiply in the derivative of x minus 8, but that's just 1. So that doesn't really contribute anything. So finally, there it is. There's the derivative. And what do we do with that now? See, that's just the first part of the problem. What do we do with that? Set it to 0, right? Okay. So you're going to set that to 0. And now you've got this equation to solve, okay? Now that looks formidable, all right, but that is not a hard equation to solve. Okay, think about the structure of the equation, not the right-hand side because its structure is 0, but that's useful, right? So the right-hand side is 0. Think about the structure of the left-hand side. What's happening on the left-hand side? Let's see. We're taking this number, we're multiplying it by e, right? And then multiplying by this, right? This minus x minus 8. So you see you have a big product there on the left-hand side. You have a big product that equals to what? 0. So when you have a product, I don't care how many factors it has in it, when you have a product that equals 0, what can you immediately deduce? What does logic tell you? What now? Something is equal to 0. That's right. One of your factors is equal to 0. Okay. Well, what are my factors here? It's this. This is a number. That ain't 0. Okay. So it's not that factor. What about e to a power? Never equals 0. Never equals 0. Okay. Yeah. E to a power never equals 0. All right. E to the 0th power is 1. It's not 0. Okay. So this is not 0. So what's going to be 0? That. And how is that 0? Well, yeah, set it equal to 0 and solve, but you can see what's going to happen. What does x have to be for this to turn out to be 0? 8, right, okay. X has got to be 8, correct? Because 8 minus 8 is 0. So there you've got it. That's it. It looks like our solution here to the derivative equals 0 is 8. What's that number called? Janiyah, what's it? What now? Yeah, that's a critical number. Yeah, okay. So there's your critical number. You can also have a critical number where the derivative is not defined, but there are no places where the derivative is undefined, okay? This expression, even though it's a complicated expression, that derivative is valid for, you can substitute any number for x that you want, okay? You're not going to end up with a bad value. You're not dividing by x. You're not taking square root of x, right? Okay? So you're not going to have any place where the derivative is undefined. But it is 0 at 8. So there's your critical number, exactly what we were hoping for, right? Okay? That's what corresponded to the picture. Yeah.
Where did the negative go?
It didn't go anywhere. It didn't really go anywhere, right? We know that minus x minus 8 has to be 0, correct? Right? But the only way that can happen is if x is 8. The minus sign is kind of irrelevant there, right? Okay. So there's our solution. All right. Okay. Now we already know that there's a critical number at 8, and that's a local maximum. We saw that from the graph. But you test that now if you really want to formally test it by doing what? It's not really easy to test, but so you'll need your calculator. But what do you do, right? So I'm not going to go through all of the steps of testing here, but what do you do there? Yeah, one that comes before 8, right, and one that comes after 8. I'm going to use 7 and 9. Those are the first ones that occurred to me there, right? And then you plug those in where? Not to the original, to the derivative, right? Okay, you plug those into the derivative, and what are you checking for? You really don't care about the number you get here. Yeah, you're just checking for the sign, right? Okay, so I think it's going to turn out that when you plug a 7 into the derivative, okay, this derivative is going to turn out to be positive. So remember, this is the derivative, right? So when you plug 7 in here, this is going to be positive. When you plug 9 in here, it's going to be negative. Just check it. You'll see when you plug 9 in here, this quantity turns out to be negative. You don't care about the size of the quantity, just the sign. It turns out to be negative. And so that means the curve is increasing over here and to the left, and then decreasing to the right, correct? Just like we saw in our Desmos graph, correct? And so we must have a local maximum at 8, right? Because we're switching from increasing to decreasing. So I skipped this step, right? But you just do that by plugging 7 and 9 into the derivative and checking the sign, okay? All right, so we have a local maximum. So now, this is the x-coordinate of the local maximum. How do you find the y-coordinate? That's right. You have to take this, right, the 8, and plug it into your original function g. Can we do that without, I think we can do that without too much work, right? What is g of 8 going to be? The reason I say not too much work is when you plug 8 in here, this all becomes what? 0. So you have e to the 0th power, which is what? 1. So you just end up with 1 over square root of 2 pi. So there is there's your second coordinate of your turning point, all right? Your local maximum turning point, right there, 1 over square root of 2 pi. See? Okay. So see, you know all those steps, right? Those are the same steps that we practice here in class. I know you practice them in Calculus 1. Just looks harder, but it's not, all right? It looks harder because this function looks terrible, but it's not a terrible function. It's an exponential function, a natural exponential function, and they have easy derivatives, okay? So that's really kind of an easy problem, actually. All right, now let's take the second derivative. Yuck. Wow. Okay, now we do have some work here. All right. Okay. All right, so this is going to be a little bit harder. How many solutions do I? No, I'm going to set this to 0, right? How many solutions do I think I have? 2, right? So we already see, right, that this is going to be a little bit more work. But now we have to take the derivative of this. Okay. All right. So now we are going to have to reach deeper into our bag of Calculus 1 derivative tricks, right? What is going to help me here? I already know that the power rule is going to come into play, right? My knowledge of taking derivative of exponential functions is going to come into play, right? But what other derivative rule is going to be important here now? What do you have here? How is this expression formed? It's a big what? Yeah, what do you call it when you multiply things together? No, that's when you raise something to an exponent, right? What? Product rule. Yeah, the product rule is going to be important here. Now, it's not because of this product, because that's a constant. That's just a constant times this exponential function. So that multiplication doesn't require you to use the product rule. It's this multiplication that requires you to use the product rule, right? Because here you have an expression involving x, and now you have another expression involving x, right? Okay. So this is the product that's going to make us use the product rule. All right. All right. So let's see if we can do that. It's going to take a few steps. So let's be careful. Let's be patient with that, and don't try to rush it. Let me erase this big brace here, because I'm going to draw another one. Here is the first factor in our product, and there is the second factor in our product, right? So those are the two things we're multiplying together in using the product rule. So how does the product rule work, right? You take what? The derivative of this, and you keep this, correct, right? the derivative of this, and you keep this, right? So, but we know what the derivative of all of this is, right? Because didn't we just take the derivative of that a minute ago? Yeah, it was the whole thing, correct, right? So, wow, let me see if I can write all that out. So I get 1 over square root of 2 pi times e to the minus x minus 8 squared over 2. And then this is going to come in there, right? Minus x minus 8. That is the derivative of this, correct? And then you keep the second factor, right? So you're going to keep a minus x minus 8. Now, that's only half of the product rule, right? What's the second half? See, you take the derivative of the first factor. That was all of this, because we found that derivative a moment ago, right? Yeah, that's the second part, right? The second part of the product rule is keep all of this, right? And then take the derivative of this, correct, right? All right, but let's go back to how we got this part. So that was the derivative of all of that, and then we kept this, correct? The minus x minus 8. Now we're going to reverse that. Keep this, and then take the derivative of the minus x minus 8. So keep all of this. So 1 over square root of 2 pi e to the minus x minus 8 squared, right, over 2. And then multiply in the derivative of the minus x minus 8. What's the derivative of minus x minus 8, though? Not 1. Negative 1, yeah. Okay. The derivative of this is negative 1. Okay. Oh, cool. So we have just a minus 1 thrown in here. So we have something like this. Wow. Let's see, can we simplify that at all? See, that looks terrible, right? But is there any way I can simplify that so that I can understand a little bit better what that is? Because what do I have to do with all of this? Remember, I just took the second derivative, right? But what am I going to do with the second derivative? Yeah, so I haven't even got to setting it equal to 0 yet, right? Okay, so if I'm going to have any hope of setting that equal to 0 and solving, let me see if we can simplify this, rewrite this a little bit. So notice there's two big things added together here, right? There's this added to this. But what's the same in both of those two terms that are added together? Isn't this part the same? Yeah, so that you can factor out, you see, okay? This part is the same in both of these terms, right? The terms are separated by this plus sign, right? So this term and this term have this part in common. So that you can factor out. Let's factor that out. So that's 1 over square root of 2 pi. We keep writing this over and over again, right? It's kind of the nature of exponential functions. So we factor that out of both terms, and what's left over then inside of those terms? So what's left in this first term? Yeah, it's this multiplied by itself, right? Correct? And then what's left in the second term? Yeah, just this minus 1, right? So what is this multiplied times itself? Yeah, it's going to be squared, right? And notice the minuses are going to cancel, right? Because you have minus times minus is plus, and then you have x minus 8 times x minus 8. That's x minus 8 squared. So you get x minus 8 squared. And then don't forget about this minus 1, though, which is still here. Well, that looks better. And what are we doing with all of that? Setting it to 0, right? Okay. All right, so we got a little bit into that, right? We have this multiplied by this, and we've got it set equal to 0. Now you're going to use your algebraic intuition again. You have a product here, this thing times what's inside the brackets here. So you have a product that equals 0. What do you know? This does not equal to 0, so what is equal to 0? The stuff inside the square brackets, that's right, okay? Because remember, e to a power is never 0. You've got it. That's another fundamental fact, okay? E to a power never 0. So, so I can just really super simplify this now. Drop this part and just write x minus 8 squared minus 1 is equal to 0. Well, let's expand this product. Oh, no, I don't even have to do that, because I can factor this already the way it's written. That's what I want to do. I want to factor because it's set equal to 0 here. But this is difference of two squares, right? This is a perfect square, because there it is. It's squared, right? And 1 is also a perfect square. What's the square root of, obviously? 1, right. So you can factor this immediately without even multiplying out here, okay? This is going to factor as the sum of the two square roots. So that would be x minus 8 plus 1, and then times the difference of the two square roots, x minus 8 minus 1. Isn't that how you factor difference of two squares? Square root, take the sum of the square roots and the difference of the square roots. We're trying to solve for x, right? That would work in this case too. But remember to take, when you take the square root of 1, remember there are two possibilities, plus and minus, right? Okay. So your solution technique is fine. Okay. But be careful about remembering numbers have two square roots, one positive and one negative. That's equivalent to what I just did here. All right. But now, what's x minus 8 plus 1? I think that's x minus 7, isn't it? And what's x minus 8 minus 1? That's x minus 9. So there you have x. Finally, wow, we got down to, here's the nub of it, right? X minus 7 times x minus 9 is equal to 0. So what is x? 7 or 9, right? There you go. Okay. So we were right. The inflection points are at 7 and 9. Okay. And so you've got, well, actually, they're potential inflection points, right? So you have a potential inflection point at 7 and g of 7, and then 9 and g of 9. You would have to plug 7 and 9 back into the original function to find the y coordinates there. And again now, to test these, right, I'm not going to test them completely, but how do you test 7, for instance? It's just analogous to testing the turning point, right? How do you test 7 to see if it really is an inflection point? Yeah, pick a number here, pick a number here, right? Oops. Pick a number on the right-hand side, and then plug these into what? Yeah, plug them into the second derivative. I think g, so I'm just guessing here, but I think g prime of 6 is going, g double prime of 6, I'm sorry, is going to be positive, and g double prime of 8 is going to be negative, I think. Okay? But you would actually have to do the arithmetic to see if that's true. But I think that's true. So that means that over here to the left of 7, the curve is concave up. Right? And then over here to the right of 7, the curve is concave down. So it looks something like this. Well, to connect these two pieces, the only way you can connect this concave down piece to this concave up piece to this concave down piece is if you have an inflection point. So I think we really do have an inflection point here at these coordinates, 7 and g of 7, whatever g of 7 turns out to actually be. So I was right. The inflection points are at 7 and 9, 1 unit away from the turning point on both the left and the right. Okay, so on just because you've heard this term before, on a bell-shaped curve like this one, the distance between the that peak in the middle, bell-shaped curves always have peaks in the middle, right? The distance between that peak in the middle and the inflection points on the left and the right, that distance is called the standard deviation. So for this curve, the standard deviation is 1 because the distance from the peak here, right, to the turning points on the left and the right, that distance is 1. So this bell-shaped curve has standard deviation 1. That's where the term standard deviation comes from. Okay, or that's one of the ways to define standard deviation. All right. Woo. There's another one? Oh no. What's the other one? Yeah, differential equation. Okay, this one takes a little bit of work too. Okay, so we're doing kind of backwards of what we normally do, right? Usually, right, we give you the function and then say what is the derivative, okay? All right, and you have all these nice rules for finding derivatives, right? But see, this problem is going to be in reverse. They're giving you the second derivative, and then they're asking you to find the original function. So whenever you have an equation that involves a function and its derivatives, that's called the differential equation. So this is an example, a very simple example of a differential equation, because you have that's an equation, right, because it has an equal mark in it, and it involves the derivative of that function f. In this case, the second derivative of that function f. Could be first derivative too, though, okay? And usually what we want to do with differential equations like this one is find the formula for the original function. Usually we don't know the formula for the original function, but we want to sort of work backwards and kind of reverse engineer what the formula for the original function was, right? So see, we're doing sort of the opposite of what we normally do. Normally we would start with the function, right, and then write down its second derivative. But here we're starting with the second derivative and writing down the function, okay? And but solving differential equations is a really important skill in all applications of mathematics, particularly in engineering. Where differential equations play a really crucial role, or certain physical sciences like chemistry, where differential equations really are important. So this is just a little practice with what it means to solve a differential equation. Okay, so well, how is it that we? What's the process that we use to undifferentiate? Right, that's what we're trying to do here. Correct? Okay. Instead of differentiating, starting with f and finding f double prime, we're starting with f double prime, right? And we're trying to undifferentiate, right? Work backwards to f. What is that process called of undifferentiation? Yeah, it's called antidifferentiation, right? Or also known as integration. So what we're going to have to do here is integrate, right? Okay, that's how you undo a derivative, correct? Is by integration. All right. So all right, y'all got to remember that. You got to remember that formula for me. 1/2 e to the x plus e to the minus x. So that's not a terrible formula. So f double prime of x is 1/2 e to the x plus e to the minus x, but we have a little bit of extra information, and this is going to be important to us. Notice that we're told that f of 0 is equal to 1, so it's going to turn out we need to have that in just a second here. So f of 0 is equal to 1, and f prime of 0, was it f prime of 0? Yeah, f prime of 0, it turns out is equal to 0. You'll see how we use this information in just a second. This is the key piece of information, though, that's really important to us. But these other pieces are also useful. These are called initial conditions. So they're telling us initially, right? Well, they're telling us information about the initial function f, correct? And its derivative. All right, so So, well, we just have to walk backwards here one step at a time. First, I have to go from the second derivative back to the first derivative. And how do you get from the second derivative to the first derivative? By doing what? Y'all said it there, what? Integration, right, okay? So I know the first derivative is going to be the antiderivative of the second derivative, right? So we'll write down our notation for the antiderivative of the second derivative, which is integral sign, right, of 1/2 e to the x plus e to the minus x, right? And then we'll do that integration. And that will tell us what the formula for f prime of x is, right? Okay, so let's see if we can do this integration. Let's factor out the 1/2, okay, because that's a constant. And now let's break this up into two separate integrals, right? Because you've got a plus sign here, so you can break this up into two integrals. One of them is just plain old e to the x, and then the other one is, don't forget the 1/2 is going to get multiplied into the second one as well. The other one is e to the minus x. All right, now this one is easy because what is the antiderivative of e to the x? E to the x, right? The antiderivative of e to the x is e to the x because the derivative of e to the x is also e to the x, right? So that's a very simple antiderivative to find. This one's just a little bit harder, but what would be the antiderivative of e to the minus x? If you want to do this, you can probably do this quickly by inspection without going through substitution process. But if you wanted to go through the substitution process, what would you substitute here? Perfect, yeah, you would let u be minus x, which means du dx is equal to what? Minus 1, which means I think dx is what? Minus du, right? And now you would substitute that. So you would have e to the u, and then minus du here, right, for dx. But this minus sign you can factor in front, right? So you have 1/2 e to the x kind of going along for the ride there. We've already done that, antiderivative. And then minus 1/2, and now the antiderivative of e to the u du, but that's so easy, right? That is e to the u again. So I have 1/2 e to the x minus 1/2 e to the u, and now I have to undo my substitution. So this is 1/2 e to the x minus what? 1/2 e to what? Negative x, right, because u was minus x. So there is your antiderivative. So there's the sort of the formula for f prime, right? Let me write it back down here. So there is the formula for the first derivative of f, but remember, there's a catch here. You have a constant in the antiderivative. Now, before you can now work backwards to find f, because now we're going to integrate this to get f, all right? But before we can do that, I have to figure out what this constant is, all right? So I need to know what that constant is. This is the clue that's going to tell me what the constant is, right? Because this is the formula for f prime, but I also know that f prime of 0 has to turn out to be 0. So let's use that piece of information to figure out what c is. So I know f prime of 0 is what? Has to be what? 0, because I was told that. But if you plug 0 into this formula, what do you get? You get 1/2 e to the 0 minus 1/2 e to the minus 0 plus this constant. What is 1/2 e to the 0? That's 1/2, because e to the 0 is 1. What's e to the minus 0? Still 1. So you have minus 1/2 again, plus this constant. But remember, all of that is equal to 0. So what's the constant equal to? 0. Yay! All right. So nice constant. It's just 0. So we can just discard that. All right. In this case, not necessary. All right. Well, so I like that. So now I know the formula for f prime, right? The formula for f prime is just this, correct? Now, what's f then? So we're just right where we want to be, right? What's f going to be now? The antiderivative of this. So the antiderivative of 1/2 e to the x minus 1/2 e to the minus x. Right? So break this up. You have 1/2. I'm going to factor the 1/2 out also. So you have antiderivative of 1/2 e to the x minus 1/2 the antiderivative of e to the minus x, right? But what's the antiderivative of this? It's e to the x, right? So you get 1/2 e to the x again. And what did this turn out to be a moment ago? Because we encountered that just a second ago, right? What happened with that? So I don't have to go through all that substitution work again. Remember what that turned out to be? Not quite the same. It had a minus sign here. Okay, so it changed this sign. So when you so now when you integrate e to the minus x, you will get e to the minus x out of this, but what's going to happen to this sign? It's going to change. So you'll get plus 1/2 e to the minus x. So if you don't trust me there, just go through those steps again of integrating e to the minus x. And this is what we're going to end up with. Plus, what do we have to throw in here? C, right. Now, I've got to figure out what C is. What's my clue, though? What's f of 0 supposed to be equal to? 1. So that's 1/2 e to, plug the 0 in here, plus 1/2 e to the, plug the 0 in again, right? So you get 1 is equal to 1/2 plus 1/2 plus C. I guess that means C is equal to what? 0, right? Okay. Because 1/2 plus 1/2 is already equal to 1. So you need this to be 0, correct? So we get another constant of 0. That won't always happen, but did in these two situations. So so you don't have to worry about this constant. So there is there's the original function. It was 1/2 e to the x plus 1/2 e to the minus x plus 0. That's the answer. So that's how you have to work backwards to find that original formula. Think you can do that again? Well, there may be one like that on the sample test. I'm not sure. I think there is one like. Is there one like one on the sample? Do you recall? I think there was one. Yeah. But we're going to do some more differential equations. So we're going to do a whole section on differential equations. So you'll see some more examples of differential equations. Okay. Again, a super important application of calculus, in particular calculus 2. Because differential equations have lots of important applications in lots of disciplines. Okay, woo! All right. So let's get back now quickly here before we have to break. So we killed some time there, but that's all right. Those are good problems. So remember, last time we were looking at differentiating and integrating log functions and exponential functions, but log functions where the base is not e. So like log base 2, that's called binary logarithm, or log base 10, that's called common logarithm. Or exponential functions where the base is not e, like 10 to the x power or 2 to the x power. Okay, those are important exponential functions where the base isn't e. And so they sometimes come up in applications, not as frequently as base e, but occasionally. All right, and so we were learning the rules for helping us differentiate and integrate such functions, right? So these were the sort of the 6 basic rules, okay? These first two and the, well, actually, these are all kind of these are kind of pairs. So the first two kind of go together. The second one is the more complicated version of the first one. The fourth one goes with the third one. This is the more complicated. 4 is the more complicated version of 3, and 6 goes with 5. 6 is the more complicated version of 5. Okay. So essentially, what this tells you is what if you take the derivative of an exponential function where the base is not e, it works like base e. You're going to repeat the exponential function, but you have to throw in one extra factor, the natural log of whatever the base is, okay? The natural log of whatever the base is. So simple, easy to differentiate exponential functions where the base is not e. Differentiating log functions where the base is not e, also easy, okay? It works like differentiating the natural log function, right? Remember, you always take the reciprocal, right, to differentiate the natural log function, except you have to, again, multiply in this factor of natural log of b, but you multiply it into the denominator, right? So it goes into the bottom here, not into the top. And then finally, if you're going to integrate an exponential function where the base is not e, they integrate just like when the base is e, right? The antiderivative of e to the x is e to the x, correct? Well, the antiderivative of b to the x is also going to be b to the x, except you have to divide out natural log of b. So you've got that extra factor in there. Remember, you're dividing that out, okay? Not multiplying it in, but dividing it out when you integrate an exponential function where, again, the base is not e, all right? But very similar to natural log and base e exponential functions. So these problems are really pretty straightforward after we practice with already with natural log and exponential functions. So let me take just a very simple example, and then we'll break and then come back with a little bit harder example. What's the antiderivative? We already did some differentiation examples last time. So what is the antiderivative of 2 to the x power? So see, that's like almost the same as the antiderivative of e to the x, right? Except it's base 2 instead of base e, correct? So how do we find the antiderivative of 2 to the x? What are we going to get there? Yeah, you're going to get 2 to the x, right? Just like when you take the antiderivative of e to the x, you get e to the x. When you take the antiderivative of 2 to the x, you get 2 to the x, but you have to adjust it how? Not times, divide out natural log of 2. So when you're doing integration, you divide out natural log of 2. If you were differentiating 2 to the x, you would get 2 to the x times the natural log of 2. But when you take the antiderivative of 2 to the x, you get 2 to the x divided by the natural log of 2. And then don't forget the constant, okay? Don't forget the constant there. That's just always part of it. Okay, let's stop for a few minutes then, but then we'll come back and we'll let you try this one. This is integrating 10 to the power, right? Okay, so going to look kind of like this one, except the power is a little bit harder. That's all, right? Okay. So we'll come back about 5 after, something like that. Okay, so let's try this one. I'll let you all try this one. So we're just integrating exponential function with base 10 rather than base 2 or base e, right? But here the exponent is a little bit trickier because it's 1 over x instead of x, right? So here you really will use a substitution to help you. And so the natural substitution here is going to be the exponent, right? 1 over x. So try that substitution and see if with that substitution this will simplify to something that to an integrand that you can integrate, right? Okay, pretty easily. Be careful about taking the derivative of 1 over x, right? How do you want to take the derivative of 1 over x? First, you want to write it how? X to the minus 1, right, okay? And then apply the power rule. Remember, you're differentiating u, right, at this step, not integrating u at this step. So, all right, so y'all try that and see what you get for, should be, I think, just a pretty easy answer, I think, in the end. And then the next example is a little bit a little bit uglier. Yeah. So how do you differentiate this?
Don't you make it to ln over x?
No, the derivative of ln of x is 1 over x, but the derivative of this is not ln of x.
Oh,
Yeah, okay. So, power rule. Think power rule. Yeah, right. Think power rule there. All right, so what'd you put there? Oh, no. Yeah, so what is the derivative of 1 over x? It's not natural log of x. The derivative of natural log of x is 1 over x, but the derivative of this is not this. So write that as x to the minus 1, and then use what? What rule will help you? Power rule. Yeah, power rule, right? Because you have a power there, correct? What did you put for? Oh, that's right. So what happened when you? Oh, lovely. Now this is, but now when you integrate, integrate first and then undo the substitution, right? So how do you integrate that? How do you integrate that? Minus, and then integral of 10 to the u. How does that integrate? Yes. Yeah. Well, actually, you can use that one. Yeah. All right. So how did you differentiate this? Oh, you use the quotient rule. You could have just used the power rule, but the quotient rule is fine. Okay. So you got. Let's see if we did the quotient rule right though. So you take did it backward. So what's the derivative of 0? What's the derivative? 0.
0.
Yeah. Minus and then is 1, right? Okay. So, is this going to be right now?
Negative now.
Oh, yeah. It's negative 1 over x squared, right? Yeah. That's correct. That's correct. Negative 1 over x squared. All right. So, lovely. Yeah. But yeah. Yes. This do the derivative here. This is u is minus power,
Yes.
right?
Yeah.
U is x to the derivative is not okay. So you may be thinking about it right, but just writing it down funny. I think that's it. But I think there's a minus sign somewhere.
Oh,
Yeah.
I forgot.
Yeah, you forgot this minus sign, right? Yeah. So y'all are getting pretty good at your substitutions. Y'all.
Oh, we're still here.
Okay, all right. So, but yeah, you're making progress there. Don't lose your. Okay, yeah. I was gonna say don't lose your minus signs. All right, yeah, that's correct. But x to the minus 2 is 1 over x squared, right? So you could write that as minus 1 over x squared.
Is this right?
I think that is correct. Yes, that's correct. Yeah. You can put this minus with this. You don't really have to have all of that in the brackets.
Yeah, okay.
So it can be just minus this and then plus a c, but that is correct. Yeah.
Thank you.
All right. So yeah, but all right. So, but what is the derivative there? You bring down the minus.
Right.
But now what do you do with that? What does that say?
Subtract.
You subtract 1, right, okay. So you got a little bit more there, all right. Did y'all ever get... Mm-hmm. So you bring this minus 1 down, right?
The x or it goes away?
No, the x is not going away, because what do you do with the exponent? When you bring the minus 1 down, what do you do with this? You subtract 1, right? So what's minus 1 minus 1?
0.
No.
Minus 1?
Yeah.
Oh, minus 2.
Right. Yeah. So you have a minus 2 there, right? So it's not gone away. It's minus x to the minus 2. But remember, x to the minus 2, you can rewrite that as what?
1 over x squared.
Right. Yeah, 1 over x squared. Correct. Okay. Well, we got sort of different stages of completion there. Sometimes that happens with substitutions. All right, so, but let's see how far y'all made it into it, if you didn't make it all the way to the end. So, let's see. So, du dx here, right, is, so some of y'all got stumped immediately on the power rule, so you got to get comfortable with the power rule. You bring the minus down, right, and then subtract. So, minus 1 minus another 1 is going to be minus 2. But the x to the minus 2, you can write that as 1 over x squared, right? You can turn that into a reciprocal. So x to the minus 2 is 1 over x squared. But this minus sign is going to stay, okay? That minus sign is going to stay. Now you have to solve this for dx, right? So solve this equation for dx. And I think you end up there with something like dx is equal to minus x squared du. All right? When you solve for dx. Now you can make your substitution. So this antiderivative is the antiderivative of 10 to the u power, because we're going to let u be 1 over x, right? Over the x squared, but then the dx is minus x squared du. And this is perfect, because now the x squareds divide out, right? But you still got this minus sign, so be careful about that. But that you can factor in front. So you have minus antiderivative of 10 to the u du. But now that is an easy antiderivative, finally. That's just an exponential function, but the base is 10, not e, right? So how does that integrate? 10 to the u, yeah, you keep the 10 to the u, but now what's the one additional thing that comes in here, because this is not base e? Yeah, divide by natural log of what? 10, right. What now? Well, let's undo the substitution for u, which is 1 over x. So I have minus 10 to the 1 over x divided by the natural log of 10, and then plus a constant. So there's our answer. Right? What were you asking me? Is the minus sign still there? The minus sign is still there.
I think she's talking about for the natural log, the base, why wouldn't it be negative 10?
Oh, okay. Because this is 10, not negative 10, right? Yeah, that's 10. So it's natural log of this base, right? Which is 10, right? Even if you brought the minus sign in front, it's the 10 that's raised to the u, not the minus sign that's raised to the u. So the minus sign is not part of the exponential function. So it's natural log of positive 10. Okay. All right, well, now we have another a hard one here. All right, so let's see if we can grind through this one. Okay, this is another important application. This is a what's called a logistic curve, and let me show you how logistic curves kind of work here. So we're using this function, so it's a little bit of a complicated formula there, right? And it's not completely, but it involves this as part of it, involves this exponential function. This is an exponential function, but the base is not e. The base is 2 here, all right? But now what we're using this formula for is we're modeling the growth in a bacteria culture after a certain amount of elapsed time. The t here is time measured in hours, and y there is the weight of the culture. which is measured in grams. Okay, so if the weight of the culture is going up, then the number of bacteria is going up, right? And this formula just predicts, right, what that weight is going to be after a certain amount of time. Okay, now the reason that we use this type of curve, this is again called the logistic curve. The reason that this curve is convenient for modeling this population is if you have population growing in a culture, then unless you have an unlimited supply of resources for that culture, right, which is like, you know, food and water and space also in your culture, the population cannot grow indefinitely, right? It can't get indefinitely large. It may grow rapidly at first, but at some point it's going to come up against these resource limits, right? The amount of space and food and water that's available. So the population growth is going to damper, right? It's going to slow down. And that's how logistic curves work often. They have shapes when you graph them like this, okay? So you can see what's happening in this logistic curve. At first it's growing rapidly, right? Okay? But then notice over here further to the right, the growth tapers off dramatically. And in fact, you have sort of kind of a natural limit here to the size of the curve, right? The curve does not go above some asymptote here on the y-axis. So that represents sort of the largest that your population can be, okay? So that's why these so-called logistic curves with complicated formulas like this are often useful for modeling populations, okay? All right, so what do we want to use that? What questions do we want to answer with that curve? Well, easy one to start with here. What's the population after 4 hours? All right, so what would our population be after 4 hours? That is really not a calculus question, right? That's more of an algebra question, because all we have to do, right, is plug in, correct? So we just have to plug in 4 into our formula. So in other words, we're trying to evaluate y, right? Okay, when t is equal to 4. That's a way of expressing that idea, evaluating this formula, right, when t is equal to 4. Okay, well, that's just a matter of plugging 4 into the formula, right? So let's see if we can get that plugged in. See if I can see all of that. So I have 1.25, and y'all are going to have to help me with some calculations here, right? And then, what is it? 1 plus 0.25, and then 2 raised to the minus 0.4 times 4, because we're going to substitute 4 for t, correct? So all of this is just arithmetic, but not going to be able to simplify that by hand, right? Really need a calculator, I think, to help you with this simplification. So we have 1.25 divided by 1 plus 0.25, and let's see, this is going to be 2 raised to minus 0.4 times 4, right? So that's minus 1.6, right? So on your calculator, you just have to get an estimate for 2 to the minus 1.6. Minus 0.4 times 4, right, is minus 1.6. So you just have to get an estimate for this quantity and then substitute it, right, into your expression to get an approximate value, at least, right, for what's the population after 4 hours. All right, so now how do you get 2 to the minus 1.6 on your calculator? If you're wondering about that, calculators are a little, different, right? But some calculators will use a caret key to give you, to raise to a power, right? So depending on your calculator, you may punch in 2 and then the caret key and then the minus 1.6, right? And then, of course, hit equal or execute. And and that can give you an approximate value here for a 2 to the minus 1.6 power. Some other calculators will have a key like this, where you have x to the y, or possibly y to the x. So again, usually what happens is you will punch in the 2 and then hit this key, and then type in minus 1.6 and then hit equal or execute, right? But make sure that on your calculator, whatever calculator you're using, you know how to do this, right? Raise an arbitrary base to an arbitrary power, okay? So because you may have to do that, right, on the homework or on a test. What is this? What is that number, approximately? Someone get that? But don't simplify all the way. I just want to know what 2 to the minus 1.6 is first. What now? 0.33? Sounds reasonable. Does that sound? Does we get some agreement with that? Raising 2 to the minus 1.6. I heard 1. Do we have some other 0.33s there? Do we have any dispute about that? Y'all need to say yes or not. I can't tell what what the verdict is here. Okay. Did more than one person get 0.33? All right. Okay. You might want to fill in a few more decimal places just to give you a little bit more accuracy, but 2 is probably the minimum number of decimal places you would use here. So you might want to try a few more there. You don't have to type in 10, but a few more decimal places with the 0.33, okay, just to give your final answer a little bit more accuracy. And notice I put the squiggly there. That means approximately equal to, because 2 to the minus 1.6 power is not exactly equal to, I don't think, I could be wrong, but I don't think it's exactly equal to 0.33, okay? All right, so this is only an approximate answer. Well, when you simplify this, then, what do you end up, when you simplify this, what do you end up getting? What now? 1.155? Does that sound right to people there? Okay. All right. So I guess our culture there after 4 hours is 1.155, right? Okay, grams. All right. All right, so that's not so much fun, right, for us. But now the next question, of course, is the one that we're really after, right? So how fast is the population changing after 4 hours? So we know the population is a little bit more than 1 gram, right, after 4 hours. But we think the population is growing. At least that's what was implied by the question, right? The population is growing. But maybe it is decreasing. But we can still answer that question right here, correct? So, of course, what's this really asking for? Rate of change, right? Which corresponds to, of course, what? In calculus? Derivative, right? Okay. So here we're looking for a rate of change, which is really just the derivative. So we're just evaluating the derivative here at t equals 4. Okay. All right. So in notation terms, right? The way you express that is you can write y prime or you can write dy dt. Those both mean the derivative, right? You're evaluating that when t is equal to 4. Okay. But now we have to find the expression for the derivative, correct? Let's go all the way back to the original function. All right, so there's the original function, and we want to find its derivative. Yuck, okay? So I'm back to reaching into my derivative bag of tricks, right, to differentiate this. And obviously, what's the first thing that pops out at you when you're looking at that formula? That is a big what? Well, it's a big expression, but what type of expression? Okay, what? Fraction, right? Okay, also known as fractions are also known as quotients, and so that suggests we may want to use what? The quotient rule. We may want to use the quotient rule. Now, so that's one way to proceed here, is to use the quotient rule, and that is perfectly okay. All right. You do not, however, in this case, have to use the quotient rule. I did write, by the way, there's the quotient rule, just as a reminder of how the quotient rule works. So there's the quotient rule. You can get away without using the quotient rule, however. If you're clever here, you can also rewrite this. Let me show you. You can rewrite this formula like this. Why are those two things the same? Notice I put a -1 here, right? So why are those two expressions really equal? Because what's that -1 telling you to do? Yeah, just pull it into the denominator, right? Okay, as a reciprocal. So I'm just writing here the denominator of this fraction raised to the -1 power, correct? So that's the same expression. The advantage of possibly writing it like this is you can avoid the quotient rule. How could you differentiate this without using the quotient rule? Use the what rule? Power rule, right, okay? So you can also use the power rule to differentiate the expression, okay? So you've got two ways of going. You can rewrite it, there may be other ways too, but at least two ways, right? You can rewrite you can rewrite your expression and then try to use the power rule, and some people prefer to do that, okay? In this case, okay, because they just like to use the power rule more than the quotient rule, or you can just immediately haul off here and use the quotient rule. All right, so take your choice there. Let's try there the quotient rule. Let me copy this. Let me copy this formula so that I can remember it. See if I got it. Oh, I think I got it there. So let's just paste it down there for reference. And then let's try to apply the quotient rule. All right. Okay, so let's see. What does the quotient rule say? All right, so remember I copied the quotient rule up there, but you can't see it. But let's recall that, right? What does the quotient rule say? If you're going to differentiate a quotient, what do? You treat the numerator and denominator separately, right? And how do you start? Derivative of the numerator, right, times the denominator. But what is the derivative of this numerator? 0, right, okay? So the derivative of 1.25 is 0. How nice. So you just have 0 times this denominator, right? Well, of course, what's that going to work out to just be? 0, right? So you really don't have to rewrite all of this denominator, but let me just put it in there for completeness, okay? All right, so you have 0 times the denominator, right? Did I write the denominator down correct? I think so. All right, so that's the first part of the quotient rule. Now what's second? Minus. Don't forget it's a minus. And now what? Yeah, keep the numerator right. So keep the 1.25. May need some extra room here. So let me write this on the second line. So keep the 1.25, right? Okay. And then we have to differentiate that darn denominator. Okay, so that's the hard part, right? Is differentiating that denominator. All right, so let's do that. Take it term by term. What's the derivative of 1? 0, right. Okay, so that's gone. Great. Got rid of that. Now, how do we differentiate this? The chain rule is going to come into play, but what's the first thing we notice here? We have what? What's this called? Yeah, we have an exponent, we have a product, but altogether, what's inside the parentheses there? What's that called? Exponential function. Exponential function, right? That's an exponential function because you have 2 raised to this expression, correct? Okay, so you need to remember how to differentiate exponential functions, all right? You don't have to use the product rule here, okay? There is a product, this is a product, right? But you don't have to use the product rule here because this is just what? A number, right? It's just a constant. So when you're multiplying, when you have a product that one of the factors is a constant, you don't have to use the product rule to differentiate that. You can just keep the constant. All right, now let's see if I can remember all of that. All right, so we're going to differentiate the bottom. That means I'm going to, remember this was the top there multiplied in. So differentiate the bottom. This is 0, so forget about the 1. So keep the point 25, right? And now differentiate the exponential function. How do you differentiate the exponential function? So how do exponential functions, what do you do with the exponential function? Yeah, right. So you're going to have natural log of 2. You're right. Okay, that's going to be in there. But what about this whole thing? It stays the same, right? You just repeat that, correct? Okay. So you have this point 25 times this again is going to still be there, 2 to the minus 0.4t. But then now I have to start adding in some extra things, right? What? Not divide by. Multiply by natural log of what? 2. Natural log 2. Because the base here is not e. So multiply by the natural log of 2. That's one thing that's necessary. And what's the second thing that I have to multiply in here? The derivative of the exponent. But that's easy, though. That's what? Negative 0.4. Right. Okay. So that is just a minus 0.4. And then that's just the top of the quotient rule, right? Because what's going to go in the bottom here? The denominator squared, right? Wow, nice, beautiful derivative here. There's the denominator squared. All right, how does all this, how does all this simplify now? Okay, what happens to all of this? 0, yay, okay. So all that's gone. So you can just wipe all of this out, right? That's all gone. And now, can we clean this up a little bit? Let's see if we can multiply some of these constants together, right? I don't know what to do with natural log of 2 because I don't know what that number is. But I have a minus 0.4 times a 0.25 times a minus 1.25. That I can multiply together with my calculator pretty easily, right? What is that? So what is that? Minus 0.4 times 0.25 times 1.25. I think I can do that in my head. Yeah, I'm pretty sure I can do that in my head. Did I do that right? Is this, do those three constants multiply together to just give me 0.125? Yes, okay. And then don't forget you have natural log of 2 multiplied in here. I don't know what that number is, so let's just leave it as natural log of 2. Eventually we'll use a calculator to estimate that, right? And then you still have the 2 to the minus 0.4t, right? And then all of this divided by what? All of this squared. So there, finally, there is kind of a nice working expression for our derivative. Woo! And I forgot, what am I going to do with this? Evaluate it where? At t equals what? 4. Yay. Okay. So now we're going to evaluate that at t equal 4. Man. Okay. So just have to use our calculator and substitute 4 into that, right? And we will get that rate of growth. By the way, is that going to be positive? I think it is, right? Because all of these, don't get fooled by that minus sign, okay? That's not going to give you a negative result, okay? When you plug 4 in for t, all of this is going to come out as positive. So that means that the population is growing, All right, the population is growing, maybe by not a very rapid amount, but after 4, the population is growing. Can y'all evaluate that for me? Oh, I think so. Y'all have just enough time. So use your calculator here to, I want an estimate for that, okay? So everyone pull out your calculator and see if you can get that value, okay? All right, that's about maybe as hard a calculator estimate as was required in the class, okay? I can't think of one that's really much more difficult than that, right? You've got to plug 4 in for t here, right? Okay, and see what you get. Just take it one step at a time. You can substitute intermediate results, but if you substitute intermediate results, make sure you use lots of decimal places, okay? So use several decimal places so that you get a nice accurate answer. Because, if you have to type that into WebAssign and you don't get enough correct decimal places, WebAssign is just mean about that, right? You think you're going to get an error? Why do you think that? You just always get an error? Okay, all right. Just take it slowly. You can write some things down on paper. Yeah, right, okay. You can write some intermediate values down on paper. Don't forget you got a paper and pencil. You don't have to do all of this in one gigantic calculator expression, okay? If you need to write some things down, do that. Did you get something?
I can't use this calculator.
Okay. All right. 2 to the only hard part is 2 to the minus 1.6. But I think it's here. Yeah. That one's got a caret key.
Yeah, that's what I used.
Yeah.
Oh, but I didn't use them.
Oh, but
this calculator's just not easy.
Well, because you can't see it? What are y'all doing? Oh, come on. You're going to plug that number 4 into that expression on a calculator, right? Okay. So I know you know how to do that. Do you have your calculator? Yeah, get out a calculator. Get out a calculator. Wow. Did y'all put in some intermediate results there? So you tried it all in one gigantic expression? Yeah, that works if you can do it there, but I hope that's it. That looks correct, though. Certainly looks like what you have there, right? Okay. Now, so you want to evaluate some things, right? Okay. So, got to plug in some values for t. You're not going to be able to do that in your head. So, yeah. Do you have a calculator with you? Do you have your phone? Do you have a calculator on your phone? You probably do, right? Okay. So try using that. I think that's correct. I saw that somewhere else. So that looks pretty good. Oh, nice. Okay. So y'all didn't do that at once, did you? Did y'all get some intermediate values and then combine them? Or did you try typing in the whole expression?
The whole expression.
Okay. Okay. Yeah. Well. Yeah. So if this looks like that expression, then that's probably correct, right? Okay. Yeah. All right. That's a little bit dangerous, though. Sometimes it's good practice to write down intermediate results, right? Okay. Because sometimes it's hard to duplicate the expression exactly. Did y'all get something there?
Yeah, but I got it wrong.
Okay. All right. Try it again there. All right. Not quite. It's off by a little bit. It's pretty close, though, but it's a little bit off. It's not too far off. So you probably just got maybe one value. I think that's okay. Yeah, that's nice. So that's good. Did you write down intermediate? I think you did, right? You did that all at once, did you?
No, I didn't.
No, you did it in several steps. Yeah, it's really good to do it, even if you don't need to do it in multiple steps and write down intermediate answers, because sometimes you're not able to immediately duplicate an expression entirely on your calculator. And if you're just addicted to doing it that way and not doing it sometimes step by step, sometimes you're going to run into problems. Okay. that way. All right, so
Is that good?
not quite.
What?
You're off by a little bit.
Just a little bit.
Yeah, and not super bad. It is a number in the hundredths. That is not 6. I think it's 0.02. So you got off. You probably missed something that you didn't multiply in there. Okay. All right. Did y'all get something there?
I got the 0.264.
That's pretty close, but I don't think it's 0.26. I think it's 0.24.
So I did the top first,
Uh-huh.
and then I did the bottom, got 1 point whatever, and then just divided these two. This one's
Yeah, so something is off a little. That's really close though, but I think it's a 0.2. Maybe I'm wrong, but I think it's 0.24.
Okay. I'll double check that out.
Yeah, so that's probably it.
So let's say we have a calculator, it doesn't let you put it all in once.
Yeah, this is fine.
What exponent
Yeah.
do you think would be fine?
I mean, how many digits
Yeah,
there?
alright, yeah.
Yeah, it's
I'd
hard
say
to know. At least 3, but the more you can use, the better. If it's just too many numbers where you have to put in lots of digits, then you may shorten it a little bit. But that's actually pretty good. 0.25 is a good estimate. Yeah, I think that one is correct. Yeah, it's something like 0.024. Did y'all find it? You can't find your mistake? Okay. All right. So y'all need to find that mistake. All right. I need. Okay. So we're out of time, right? Okay. I think the answer there is approximately 0.024. Okay, I saw that several times, so I think that is it. Okay, so if you got that either immediately or indirectly, that's good. If you're off by a little bit, okay, then you need to practice that, because that's something that's going to hurt you on your test. If you're really not trying to do it, I don't know what to tell you. Okay, this is not the class for you. All right, not the major either. Okay. I'll see you guys Wednesday.